So last week we discussed, in the last session we discussed resistance, right? And about superconductors also, I guess. So today we are discussing about system of resistors. So that is a combination of resistors, right? So today's topic, system of resistors. So under that subtopic, equivalent resistance. Already we might know what is an equivalent resistance is. When a network is given, when a network of resistors is given, we find instead of that whole network, how we can replace it with a single resistor. So the equivalent resistance, the equivalent resistance of a network will be the single resistor that can replace the entire network. So there are mainly two types of combinations that we use. There are mainly two types of combinations to form a network of resistors. So there are several methods, but among them, these two are special. So the first combination, first one, it is series connection or the series combination. Series combination. Second, parallel combination. So let us look at what is series combination. So in series combination, Let's say we have three resistors. R1, R2, and R3. Instead of these three resistors, we are going to replace a single resistor. Let's say this is R equivalent. The current we supply, through this is I, and the current through this is also I. Now this combination shouldn't make any changes to the circuit. So the potential difference across this should be V. Between these 2 points, it has to be V. Now I know that each and every resistor, there is going to be a drop across each and every resistor. Let's say the drop across this is V1. Drop across this is V1, and across this is V2, and across this is V3. We know that V is equal V1 plus V2 plus V3. But V is equal IR. Here, instead of V, I can straight away write I into R equivalent. So V equal IR, I into R equivalent. This is equal, drop across this, that is I into R1 plus I into R2 plus I into R3, and so on. So I cancels. We come to the important equation. R equivalent is equal R1 plus R2 plus R3. So when we have resistors in series, the equivalent resistance is sum of them. So when do we call a resistor is in series? We should have the same current flowing through those resistors. So we can tell if a number of resistors, if a number of resistors are connected such that the same current such that the same current flows through each resistor, then they are connected in series. They are connected in series. Okay. So let's write a note. Note number 1. If we have n number of resistors, then R equivalent is equal sigma of Ri. I is equal 1 to n. We have to just add all of them together. Note number 2. Let's say that we have 3 resistors, R1, R2, and R3, such that R1 is less than R2, which is less than R3. So here R3 is the highest resistance. Then we have the equivalent. R equivalent is greater than R3. So from this, we can get an idea. The equivalent resistance of a series combination is always greater than the highest resistance. Okay. Note number 3. Again, we have 3 resistors, R1, R2, and R3, such that R1, R2, and R3 are like this. R3 is greatest. Let's say the potential difference across this is V1, and across this is V2, and across this is V3. We know that V is equal IR, but in series combination, I is same through each resistor. Therefore, V proportional to R. Hence, V1 V3, V2, and V1. This will be the increasing order of potential difference. Is it clear up to this? Okay. Shahama, how about you? So next, let's look at parallel combination. Parallel combination. So in parallel combination, let's say we have three resistors. R1, R2, and R3. R1, R2, and R3. And R equivalent. So here, if we supply the current I, this time the current will divide into I1, I2, and I3. So it is not useful if I use, yeah, okay, current will divide. But how about the potential difference across each resistor? Here also I supply current I. The potential difference across this will be V. Across this is also V. Here also it's V. And here also it's V. So the potential difference is same in each and every resistor. Look, because it is connected to the same points. Okay, the resistors are connected to the same points, therefore potential difference is same. Now, considering the current, I can write that I is equal I1 plus I2 plus I3. But we know that, but V is equal IR. Instead of I can use V over R. So here we have, instead of I'll use V over R equivalent. V over R equivalent. This is equal, instead of I1, V over R1 plus V over R2 plus V over R3. So these values cancel. Then we come to this equation. 1 over R, 1 over R equivalent is equal 1 over R1 plus 1 over R2 plus 1 over R3. So when we call a combination is parallel, if a number of resistors, if a number of resistors are connected such that the potential difference the potential difference across each resistor is maintained the same or is the same. Then the combination is parallel. Not number one, R1, Rn. So when we have n number of resistors connected in series, one over R equivalent is equal 1 over R1 plus 1 over R2 plus so on until 1 over Rn. If R1 equal R2 equal so on until Rn, then 1 over R equivalent is equal n over R. This is equal to R. So R equivalent is equal R over N. Did you get this idea? Second, when we have a few resistors, I would say R1, R2, and R3. R1, R2, and R3, such that R1 is less than R2, which is less than R3. Then R equivalent is less than R1. So we can tell the the equivalent resistance of of parallel combination is less than the least resistance. Is that clear? Let's say you have 100 and 1000, then the equivalent will be for sure less than 1. Noted. Note number 3. Let's say we have 3 resistors. R1, R2, and R3. The current through each resistor I1, I2, and I3. If we look for the current through each resistor, let's see, V is equal IR. But for for parallel combination, V is constant. For V is same. Therefore, IR is equal to a constant. IR is equal to constant. Therefore, I is inversely proportional to R. So here, such that R1, R2, and R3. So if we compare the current, through each resistor, that will be I1 is greater than I2, which is greater than I3. Let's write this here. It's all right. Okay. Is this point clear? So these are very important small tricks that will help you do questions. Probably MCQ questions. You should understand the previous and this. In series combination, always the resistance is greater than the greatest. And in parallel, equivalent is lesser than the lowest. And also the relationship between potential and resistance, current and resistance. So that is important. It should help you. So far, is it clear and have any doubts? Okay, Shahama, clear? So shall we try some examples? Example 1. Eight ohms, 6 ohm and 3 ohm. We have to find the equivalent. So here we can solve these two resistors first. This is how you do. You somehow try to find out a parallel or a series relationship. Okay. Here, what do you think about 8 and 6? These 8 and 6, are they in series? They are not in series. Okay, what is the condition to be in series? To be in series, the same current has to flow. If you supply current from this side, here the current will come to this junction and it will divide, right? Then they are not in series. Okay, now you can find these two parallel, solve those two, and then the equivalent of this will come in series to this. What is the equivalent of 6 and 3? Mm, 2 ohms, right? So this is equal and this is equal to 10 ohm. Here, here you can find, I'll say this is R dash. R dash is equal, sorry, 1 over R dash is equal 1 over 3 plus 1 over 6. This is equal 3 over 6, which is equal to half. Then R dash is equal to 2. Otherwise, you can straight away do this way. Otherwise, 1 over R is equal 1 over R1 plus 1 over R2. So 1 over R is equal R1 plus R2 over R1 R2. So R is equal R1 R2 over R1 plus R2. So using this equation also you can find the answer by mind. So you get the product over sum. The product is 18, sum is 19, therefore 18 over 2, sorry, 18 over 9, that is 2. This equation also will be helpful. Noted.